So now we move on to electromagnetism. Find out what the difference is here. Electromagnetism is the production of an electron as a magnetic field by current in a conductor. So electromagnetism requires a flow of electrical current. Current produces a magnetic field called an electromagnetic field around a conductor as shown. The invisible lines of force of the magnetic field form a concentric circular pattern around the conductor and are continuous along its length. Unlike the bar magnet, the magnetic field surrounding a wire does not have a north or a south pole. The direction of the lines of force surrounding the conductor, shown in the figure, is for conventional current. The lines are in a clockwise direction. When current is reversed, the magnetic field lines are in a counterclockwise direction. So the good thing about electromagnetic fields and electromagnetism is that stopping and starting of current or changing its direction causes the field to expand and collapse, expand and collapse. And this is where we get the vehicle, if you will, for a motor. Although the magnetic field cannot be seen, it's capable of producing visible effects. For example, if a current-carrying wire is inserted through a sheet of paper in a perpendicular direction, iron filings placed on the surface of the paper arrange themselves along the magnetic lines of force in concentric rings instead of what we saw with a magnet. Okay, so we can see here on the figure here, as the current is moving along the conductor here, we have a clockwise pattern of magnetic lines of force around the conductor. Down here in this figure, we can see that it shows that with the current moving in the direction of the hand and thumb, we can use what's called the right-hand rule. The right-hand rule is used for conventional current. So it's an aid to remembering the direction of the lines of force as illustrated in the figure. Imagine that you're grasping a conductor in your right hand and your thumb pointing in the direction of current. And that becomes very, very important when we start dealing with vectors associated with magnetic fields. So what properties do we have associated with electromagnetics? Permeability, the little mu letter, the thing that we use for micro, we also use mu for the permeability. The permeability is the ease with which a magnetic field can be established in a given material and is measured as the permeability of that material. The higher the permeability, the more easily a magnetic field can be established. So if you've got a material that's permeable, then you have a good chance of establishing a magnetic field. The Greek symbol of permeability, mu, and its value varies depending on the type of material. The permeability of a vacuum, mu naught, is 4 pi times 10 to the minus 7th Webers per ampere turn times meters. Okay? Webers per ampere turn meters, and is used as a reference. Ferromagnetic materials typically have permeabilities hundreds of times larger than that of a vacuum, indicating that a magnetic field can be set up with relative ease in these materials. Ferromagnetic materials include iron, steel, nickel, cobalt, and other materials. So to determine what kind of permeability we've got, we've also established something called the relative permeability, or mu r. Mu r of a material is the ratio then of the absolute permeability to the permeability of a vacuum. So we have mu by mu naught gives us the relative permeability mu r. Because it's a ratio of permeabilities, again, mu r is dimensionless. Typical magnetic materials such as iron have a relative permeability of a few hundred. Highly permeable materials can have a relative permeability as high as 100,000. So there's our first term. Our next term, something called reluctance, a stylized R. The opposition to the establishment of a magnetic field in a material then is called its reluctance. So if you're reluctant to do something, the more you're reluctant, the higher your reluctance. The value of reluctance is directly proportional to the length of the magnetic path and inversely proportional to the permeability and to the cross-sectional area of the material as expressed by this relationship. So reluctance is equal to length divided by mu A. Reluctance in magnetic circuits is analogous to resistance in electric circuits. The unit of reluctance can be derived using L in meters, A area in meters squared, and mu in Webers per ampere turn meters as follows. So we lay it out here. Reluctance is equal to L over mu A, which is equal to, there's our expanded units, and we end up then, when we start moving things around, the area, the ampere turns, make sure I've got this right, cross section. Okay, this is the ampere turns divided by Webers. Okay, even I get confused sometimes. So AT is the ampere turn divided by a Weber for our measure. Sorry about that. So similar to in equation 2, the resistance of a wire, where the resistance is equal to rho L by the area, in this case, the reciprocal of resistivity, rho, is conductivity, sigma. That's the little letter for sigma. By substituting 1 over sigma for rho, the equation then can be written as the resistance is equal to L by sigma A. Okay, compare this last equation for wire resistance with that of equation 10.3. Okay, so there's our relationship. All right, so you get the idea here. We're establishing relationships associated with magnetism or electromagnetism with that of electric circuits. So let's do some quick calculations here. Calculate the reluctance of a torus, which is a donut-shaped core, made of a low-carbon steel. The inner radius of the torus is 1 3/4 centimeters, and the outer radius of the torus is 2 1/4 centimeters. Assume the permeability of low-carbon steel is 2 times 10 to the minus 4th Webers per ampere turn meters. So first we must convert centimeters to meters because we want it in SI units before we calculate the area and length. From the dimensions given, the thickness, the diameter, is 1/2 centimeter or 5/thousandths this time, 5/1000ths of a meter. Thus the cross-sectional area is equal to pi r squared. So the value of r was 0.25, or actually 0.0025 squared, which gives us 1.96 times 10 to the minus 5th meters squared. The length is equal to the circumference of the torus measured at the average radius of 2 centimeters or 2/100ths of a meter. So the length is equal to the circumference, which is equal to 2 pi times the radius, which gives us about 1/8 of a meter, 0.125 of a meter. Substituting the values then into the equation, reluctance is equal to the length over mu A. Our values then become 0.125, or 1/8 of a meter, divided by 2 times 10 to the minus 4th Webers per ampere turn meters, times 1.96 times 10 to the minus 5th for our surface area, meters squared, gives us 31.9 times 10 to the 6 ampere turn per Weber. Okay, so that's our reluctance. Let's look at the next one. Mild steel has a relative permeability of 800. Again, no units. Calculate the reluctance of a mild steel core that has a length of 10 centimeters and a cross section of 1 centimeters times 1.2 centimeters. First, determine the permeability of mild steel. So the permeability mu is equal to mu naught times mu r. There's our relationships. We get a value of 1 times 10 to the minus third Webers per ampere turn meters. Next, we can convert the length to meters and the area to square meters. Okay, so the length 10 centimeters gives us 1/10 of a meter. The cross-sectional area then is 1.2 times 10 to the minus fourth meters squared. Substituting those values then into the equation for reluctance, L by mu A, we get 8.33 times 10 to the fifth ampere turns per Weber. Okay, so let's take a break here. Think about that. There's a lot of information given in these couple of pages. When we come back, we're going to look at the correlation between magnetomotive force and something we've seen before, the electromotive force, which is our voltage in electric circuits.